Hello everybody, welcome to a video in linear approximations. The examples are taken from Thomas's calculus book and chapter 3 of that book, and let's look at some applications of derivatives. Let's say we have a function y equals square root of x. So if we draw this function, we'll see that it is of this nature, x and y, and this is y equals square root of x. So if we get the derivative, say if y is equal to square root of x, this is equal to x to the power half, and the derivative would be dy over dx would be half x. The half minus 1 is minus half. So that should be equal to 1 over 2x square root of x. So this is a function of that gives, it's a function of gradients. It's called a gradient function. In other words, for every x, you can determine what the gradient at that position is from the derivative function. So, for example, when x is equal to 1, the gradient or the line that just touches the x-axis, not the x-axis, the graph, the line just touches the graph, the angle that line makes with the x-axis is the gradient. That's the line that touches this point at x equals 1, just one point. That the gradient or the angle that makes with the x-axis is the gradient. When x is equal to 4, the gradient would be, if you draw a line that touches the graph just at x equals 4, and the angle that it makes with the x-axis is the gradient. So this gradient varies according to the position of x. You see the angle that this line makes with the x-axis at different locations varies. So this could be x equals half. So let's take some examples. And of course, if the x-axis is time, it would give you the rate of change. The derivative would give you the rate of change at any location. When you substitute the x based on x, you can get the rate of change at any location. So let's say we will make a table. So this is x and this is y equals x square root of x. That's this function, and we'll write the derivative of it. So dy over dx or is equal to y dash. That's another way of writing dy over dx is 1 over 2 square root of 2x. That's what we learned. So when x is equal to 1, we get the location of, when x is equal to 1, we get the location on this axis, on the y-axis, by substituting x equal to x to this equation. When x is equal to 1, we get y is equal to 1. Then if you want to find the angle this line makes with the x-axis, with the horizontal, that's the gradient, we just substitute 1 to this. So when you substitute 1, you get 2. That's the gradient at x equals 1. Once we have the gradient, we can write the tangent, the equation of the tangent. The equation of the tangent would be y minus y0 over x minus x0 equal dy over dx at x0. So if you get the gradient at x0, and if you write this, find a y0 and x0, we can write the equation of the tangent. So if we assume that this is x0 and y0, then you can get the value, the tangent, equation of the tangent at this x0, y0. So we can write it as y minus 1, y0 is 1, over x minus 1 equals the gradient at x0, x0 is half. So we can also write this as dy over dx at x0. If we call this x0 and y0, we can write this is the dy over the gradient at x0, because we substitute 1 here, which is x0. So if we simplify this, we get y minus 1 equals x over 2 minus 1 over 2. So we get from this, we get y equals x over 2 plus half. That's the tangent, equation of the tangent at x0, y0. So let's assume let's do the same thing for another set of x0s and y0s. So let's say x0, any value on the x-axis, x0 is equal to 4. And if x0 is equal to 4, y0 would be, when you substitute it to here, you get 2. Then dy over dx, this is the gradient at x0. Here the x0 is 4, is equal to 1 over 4. So let's get the equation of the tangent, which is y minus y0 over x minus x0 is equal to derivative at x0. So this gives us an equation to y minus 2 over x minus 4 equals quarter. So that is, this is y minus 2 equals quarter times x minus 4. So you can get the equation would be y equals x over 4, this is minus 1, plus 3. So plus 1. That's the equation of the tangent at x equals 4. So let's continue to do more examples. So let's say this is x, similar to the previous example that I did. So if this is x, if y is equal to, we know it's square root of x, and we found that dy over dx is equal to 1 over 2 square root of x. This is the gradient. So when we have already worked on x equals 1 and 4, let's do x equals 9. When x is equal to 9, the y, we can call this x0. When x0 is equal to 9, y0 is equal to 3. And dy over dx at x0, all you do is substitute x0 to this place. This is 1 over 6. So once we have the 1 over 6, let me separate this out. the gradient, or rather the equation of the tangent of the tangent at x0 is y x0, we can say x0 y0 is y minus y0 over x minus x0 equals to dy over dx at x0. So this is equal to 1 over 6. So let's substitute y0 equal x0 from these values. So we have y minus 3 over x minus 9 equal to 1 over 6, and that is y minus 3 is equal to x over 6 minus 9 over 6, and that would give us y equals x over 6 plus 3 over 2. That is the equation of the tangent at x equals 9 and y equals 3. So let's take another example. When x is equal to 16, we call this x0. When x is equal to 16, y0 would be 4, and dy over dx at x0, which is 16, is equal to 1 over 8. And then if you write the equation of the tangent at x equals 16, y equals 4 is y minus y0 over x minus x0 is equal to dy over dx at x0, which is equal to, the value here is equal to 1 over 8. So we have, if we substitute y0 and x0, we have y minus 4 is equal to x, or we'll write it down here, x minus 16 is equal to 1 over 8, and this can be written as y minus 4 equals x minus 16 over 8, and y is equal to x over 8 plus 2. So that is the equation of the tangent at x equal to 16. Let's look at the function again. So we know this is the graph of y equals square root of x, and we know the derivative of this is this, and we saw that at x equals 1, we found the equation of the tangent at x equals 1 and y equals 1, and x equals 2 and x equals 4 and y equals 2, we found the tangent, equation of the tangent by getting the gradient of the tangent at x equals 4. So you see that the equation of the tangent varies according to the location of x, because the gradient varies according to x, and the equation of the tangent varies according to the location of x0 and x and y. So let's look at an application. To explain what linear approximation is, first we'll start with an example. So y is equal to square root of x. Let's look at y equals to square root of x. So if we want to find the value of square root of 3, this is hard. We need a calculator to get the value of x at square root of 3. So for instances like that, let's look at some other way of approximating the value of square root of 3. So let's first look at the function y equals square root of x. And this is the function y equals square root of x. If this is 3 and this is 4, this point is 4 and on the x-axis, and the value here would be the value that we are looking for. So this value here would be square root of 3. That's the value we are looking for. But instead, we can use a method of approximation by calculating the value at 4, which is y is equal to, at x is equal to 4, y is equal to 2. If at x equals 4, y is equal to 2, when x is equal to 4, y is equal to, we can get the line, the tangential line. The tangent at x equals 4, y equals 2. So instead of getting the value at x equals square root of 3, what we can do is use this tangent and look at and substitute the value to the tangential line and see what the value here is, and that would be a linear approximation for square root of 3, which is this point. So how do we do this? First, let's see how we get the tangential line. We did that. We found that the tangent, the equation for the tangent was y equals x over 4 plus 1. This was the tangent at x equals 4. The tangent at x equals 4 was this. Now, this line, that's the equation of this line. Let me write it down. Equation was y equals x over 4 plus 1. And if we substitute 3, x equals 3, we would get the value at this point. So if we substitute x equals 3 on this tangent, we get y equals 3 over 4 plus 1, and this is 1.75. So the value on the tangent at 3 is 1.75, and that is considered an approximation for square root of 3. So again, let me emphasize, let me draw this again. I'll zoom in. So if we zoom in, maybe I should draw it bigger. So if we zoom in to this point, we have that's your 3, and let's say this is 4. X equals 3 and x equals 4. This point would be square root of 3 because that's y equals square root of x. And if we draw the tangent line, it would be, that would be the tangent, and that's the place where it touches, the tangent touches the y equals square root of x, and this point would be 1.75 because the equation of the tangent is y equals x over 4 plus 1. That's the equation of tangent, and when we put x equals 3, we get 1.75. And we say that that's a linear approximation for square root of 3. Now, we didn't need a calculator to get the value of this. All we needed was to derive the tangent line and substitute x equals 3. So that that is considered a better way or approximate way to get values like square root of 3. So next we'll calculate the square root of 3 using a calculator. The calculator square root of 3 would be 1.3205. That's an approximate value. This is a good approximate value for the real square root of 3. So what we did here was we calculated a tangent of a value that we know, which is 4. When we know x, when x is equal to 4, we know y is equal to 2, and we got the tangent for that, and then we extended the line and substituted 3 to get the value, an approximate value for square root of 3. Because square root of 3, we could not just calculate square root of 3. So let's say we are asked to find a linear approximation to square root of 3. So first thing we do is find a representative function. That means you find a, a equation like y equals square root of x. Basically, you substitute a variable instead of this value. Then you find a point on the function you can easily find or know the answer for. So here we know when x is equal to 4, we know y is equal to 2 in this function. X is equal to 4, y is equal to 2. And we can also call this x naught and y naught. Then we are asked to find the tangent line. To find the tangent, we know we have to do the following. First thing, we need to find the derivative. Derivative of the function of derivative or the derivative. So we know that dy of dn over dx of this function is, we know it is half square root of x. We know that. So we find the derivative. Then we find the gradient at x0. We have decided that this is x0 because we know that y0 for x0. So the gradient at x0. Then we find the tangential line, equation of the tangent. Equation of the tangent. So that is a line through x0, y0 with a gradient of dy over dx at x0, right? And then what we do is substitute 3 for x in this line. Let's do this from the beginning. So let's say we'll do all those 4 steps one by one. The first step is to find the linear approximation. We find the representative function, which is y equals square root of x. 2, we then find a known function, a known value. We know that when x is equal to 4, y is equal to 2. And we'll also call them y0, x0. Next thing is we find the tangential line. So 3 tangent. For that, we get the derivative. Y dash or dy over dx, we have seen that it is square root of 2 square root of x. And then we do is we get the gradient at x equals 0, x equals 4 or x0. Gradient at x equals 0 is equal to dy over dx at x0. So we know x0 is 4. So gradient is equal to 1 over 2 square root of 4, which is equal to 1 over 4. That's the gradient at x equals 4. Next thing is we write the tangent equation of the tangent. Is equal to y minus y0 over x minus x0 equals dy over dx at x0. We know dy over dx at x0 is this. So we write the equation as y minus 2 over x minus 4 is equal to 1/4. And we have done this before. We see that y equals x over 4 plus 1. This is a very important step. So now that we have the tangential line, next thing we do here is instead of substituting 3 here and needing a calculator to get that, what we do is substitute the 3 here. So we get y equals 3 over 4 plus 1, which is equal to 1.75. So those are the steps to finding the linear approximation. There are 4 steps to finding the linear approximation of a function. So we'll do another example to see if we can find the linear approximation to another function. So we have asked to find the linear approximation for cos 0.1. Now we don't know the value of cos 0.1. So first thing we do is write a function. Function is y equals cos x. Next, we find a known value. We know that when x is equal to 0, we know y cos 0 is equal to 1. Cos 0 is equal to 1. When x is equal to, I'll show you the graph of cos 0. Cos is a graph like this. So when x is equal to 0, cos x is equal to 1. Then we have to get the find the tangent equation of the tangent, which we need the derivative. So dy over dx is, we know the derivative of cos x is minus sin x. I'll write the sign properly. So next we need the gradient at x0. So we will call this x0, y0. And now we have to find the gradient at x0, y0. So x0 is 0. So dy over dx at x0 is equal to sine 0 is 0 minus sine 0 is 0. So we know the gradient at x equals 0 is 0. So if you draw the sine graph is of this nature. So when x is equal to 0, sine x is 0. Next thing we want to do is write, this is the grade. We write the tangent. Equation of the tangent. Equation of the tangent is y minus y0 over x minus x0 is equal to dy over dx at x0. So we know dy at dx at x0 is equal to 0. And when x is equal to 0, we know from this plus x, when x is equal to 0, y is equal to 1. So we substitute it there. So when y minus 1 over x minus 0 is equal to 0, this implies y equals 1. So that's the equation of the tangent. Then 4 we say we substitute 0.1 to the tangent line. So the tangent here does not have any x value, so there is no place to substitute the x, but the value is equal to 1. So when x is equal to 0, y is equal to, so 1 is the approximate value for cos 0.1. So let me explain this as a graph. We have seen that cos graph is of this nature. Pi over 2 pi, and we saw that if this is x and y, we saw that at x equals 0, the tangential line is y equals 0, 1. Y equals 1. So this is at 0 and this is at 0.1. We are told to find the cos value. So instead of finding the cos value, we substitute that x equals 0.1 to the tangent, which is an approximate value to this. If you zoom in to this area, you will see that you have and the tangent line. So instead of getting this value, we take the value at the tangent line. Let's do another example. Let's say we have to find the linear approximation of e to the power 0. The first thing we do is we find a function. Function should be y equals e to the power x. Then to find known values. So we know when x is equal to 0, we call that x0. We know e to the power 0 is equal to 1. So we know the values of x0, y0, it's 0 and 1. Then third, we need to get the tangent, equation of the tangent, for which we get the derivative dy over dx is equal to ex, because the derivative of ex is ex. Then we want to find the gradient at x0. Gradient at x0 is dy over dx at x0 is equal to e to the power 0 is equal to 1. Then we get the equation of the tangent. So the equation of the tangent is y minus y0 over x minus x0 is equal to dy over dx at x0. So we know x0 and y0. Let's substitute it. Y minus 1, x minus 0 is equal to 1. So we see the equation of the tangent is y equals x plus 1. Now then the fourth step here is substitute uh, 0.1 to the line of tangent. to y equals x plus 1. So the value would be approximate value would be 0.1 plus 1 is 1 plus is equal to 1.1. That's the approximate value of e to the power 0.1. So in summary, we looked at three approximations. Y equals, it was root 3 cos 0.1 and e to the power 0.1. For root 3, we assumed the function was y equals square root of x. We knew the value of when x is equal to 4, we knew y was 2. We drew a tangent. Instead of this value, which is square root of 3, we approximated the value by drawing the tangent and substituting 3 to the tangent. And here, this is cos x. We knew the value of cos 0. That's when x equals 0. We drew a tangent at x equals 0. And instead of getting the value cos 0.1, we substituted the value 0.1 to x to the tangential line and got this value to approximate cos 0.1, the value that I show in orange. So this value was used to approximate cos 0.1. And e to the power x, did not know how to evaluate e to the power 1. So we knew the value is 0 and we drew a tangential line and found the equation of the tangent, and we substituted 0.1 to the equation of the tangent and use this approximation, this point on the tangential line at x equals 0.1 to approximate e to the power 0.1. Okay? I hope you enjoyed this. Please go and have a look at the chapter 3 equation examples under linear approximation.